Hello, welcome back for lesson 5.6. We are going to look at graphs of the other four trig functions. And the first two we're going to look at are the tangent and the cotangent function. And you can see here that tangent is related to sine and cosine, as tangent is the ratio of sine over cosine. And so it creates this function here that has these vertical asymptotes. So it moves from left to right, it moves in the upward direction. So that's something that you would probably draw like a basic picture for yourself on your note sheets, because you can see if you go a couple pages down, you can see the cotangent picture. Cotangent is the ratio of cosine over sine, and that picture is on page 472, and that goes from left to right. It goes in a downward like squiggle. So I would definitely have those basic graphs on your note sheet for the next exam, just so you've got the basic ones. I am going to go to, you can see all the basic pieces of code, the graphs of the tangent and cotangent in the book. It goes through their range. The domain for both is all real numbers except for n pi for cotangent, and for tangent it's all real numbers except for 2n plus 1 pi over 2. But you don't have to worry about that too much because we're mainly using Desmos for graphing and just getting the basic understanding of what the picture should look like. Okay, so let's go ahead and look at Desmos. You'll see it's all saved. You can see the link in Canvas for that. So the first one I'd like to look at is number 5. It's looking at a cotangent function. I'm trying to do just a grouping of all 4 new graphs in this lesson today. So I'm trying to hit some of each. And so the first one is just a cotangent, and it's a vertical shift. So I'm going to put in the basic y equals cotangent of x function. So you can see that here. And then I'm going to turn on the one for number 5 in blue. And you can see it's just a shift up, 1.5, a vertical shift up. And I'm going to turn those off. And then number 9 is the secant function, the graph of secant of x minus 1 pi over 2. So it is a shift to the right. And so I'm going to put in a basic y equals secant x function. So you can see that. And then I'm going to turn on the shifted one here, and that's going to be in black. I'm going to turn that. I'm going to change the color. There we go. Okay, so the blue is the natural secant, and then the red is the shifted right by pi over 2. So our shifts and our stretches, they all look just like they did earlier in the semester with our quadratic functions, but also in 5.5 with the sine and cosine graphs. So I'm going to turn off those two. And now I'm going to look for number 15. Let's look at the basic cosecant graph here. That's what that looks like in green. And then you can see in number 15, it says 2 times the cosecant. So that's going to be a vertical stretch in purple. And you can see where it gets skinnier and it's vertically skinnier and up. Okay, so we've looked at cotangent. So I'm going to turn these off, and I'm going to go up and click on the cotangent again. I'm going to turn that on in red. And now number 17 is a stretch, a vertical stretch, but notice it's going in the other direction, and that's because it's a negative to cotangent. Okay. I'm going to turn on the cosecant again. I'm going to go up and turn off that cotangent. So turn on cosecant because number 23, so here's our regular cosecant, and cosecant in 23 is a horizontal stretch. And there's that horizontal stretch there. And then I'm going to turn off the cosecant, and then 25 is the tangent. It is shifted left pi over 4 and then up. So let's just look at the basic y equals tangent function. And there's our regular tangent function. And then here's our one from 25. It shifted left and up 1. So fun. Okay. So if we go to the book and look at number 35, let's go down to the problems here. 35 through 38 are giving us the graph, and it's asking us to try to figure out what it is with it shifting. And it says it can only be a times tangent b of x or a times cotangent of b of x. So either a horizontal shift or a vertical shift. I'm sorry, horizontal or vertical stretch or compression. Sorry about that. So you can see in 35 that it goes from left to right, it's going down. So that's going to give me an indicator that it is cotangent. And if we go back and look at the cotangent on page 472, you can see that that's it crosses at pi over 6. When it's been shifted. So the regular pi over, the regular cotangent is at the top of page 472, and it is, let's just take you there. Right here. It's crossing at -3 pi over 2. Okay, but the one here on number 35 is crossing at -pi over 4. So it's going to be shifted a little. It looks like it is okay, so it's a cotangent, and if we square it, if we double it, it's going to stretch it, vertical stretch. So let's just go to here. Let's just put in cotangent of x, and we're just going to play around with what it looks like. Let's turn these other ones off here. Let's turn this on. Here's our cotangent. Okay. Our basic cotangent. Now let's play around with it. Y equals, it said it could only be a vertical stretch. So let's just do a 2 times cotangent and see what happens. That made it actually more straight, and that's not really what it did. So I don't think it's a 2 on a vertical stretch. What if it's a 1/2 compression of cotangent? That is just making it more of a turn, but it's still at -pi over 2, where the one in the book is at pi over 4. So it's not going to be a vertical stretch or compression. So let's go on the inside and do a horizontal. And let's see what that does. Oh, it is crossing at -pi over 4. So it looks like we have the winner. Y equals cotangent of 2x right here. That is the winner for 35. Okay, let's turn those off. Okay, let's look at number 37 in the book. So 37 is going from left to right. It's going up, it's increasing, and that is what a natural tangent looks like. And it's going through the origin. Okay, so let's go draw just a regular y equals tangent and see what that looks like. Okay, and that goes through the origin. And then it hits 2. Right about there, about 1 and 2. So let's just go back to the picture in the book. So the picture in the book is 0, but it's not hitting 2 till way over here at pi. So it's definitely flatter. So I think it's going to be a compression. So let's just do a y equals a vertical stretch 2 tan x and see what that looks like. Let's turn it on. So that's the green. That's definitely making it more vertical. So it's not that. Let's do 1 divided by, let's 2. Oh, no, I didn't mean to do that. Okay, so a compression. Oh, that looks like that might be it. It's still 0, 0. So we have to remember that pi over 2 is going to be about 1.7. So that's not it, because our graph says that pi over 2, and it's hitting 2 over at about pi. And this is hitting 2 before that. So that's not, I don't think it is the vertical. Let's do the horizontal on the inside. Let's do 2. That's too high again. Maybe it's a 1/2. Maybe it's a compression. Oops. 1/2. Does that look more like it? So, and it has an asymptote at, oh, I know. The asymptote is at 3/2 pi. But this asymptote is not at that. 3/2 pi. So the next one is at pi, 0 and pi. So let's change this. Let's do pi over 2. Pi over 2. No, that's making it sharper. Over 6. Oh. See what that is that today. Three pi over 2. That's at pi. I'm looking at the green ones. It's at 6. So its period is at -3 pi over 2. Let's go to tangents. Period. Right here. Okay. tangent's period is a pi. So if we know it starts at 0, then it's going to go pi over 2 this way and pi over 2 that way. Because it should be a pi. Its period is pi. And well, we can try pi over 3. That's the pi over 6. Maybe it's not so much. Let's try pi over 3. These are not any different than the second thing. It's the pi that's making it. Let's do it instead of, maybe try the 1/2. Oh, that's getting a little bit closer. So there is the because 3 pi over 2, we can see where the horizontal shift is at 3 pi over 2. And 3 pi over 2 is 3. You can find out what that number is. Pi divided by 2. It's 4.71. So we can see, so we could have it make a table and see what the asymptote is at. Okay, so we know it's in between 4 and 5. So if I did 4.5, 4.6, 4.7, it's getting infinitely large, and we know that 3 pi over 2 is 4.71. So we are close. So I think our function that we have is tangent 1/3 pi, 1/3 x is pretty close. Wow. Okay. So the last problem that I wanted to do was number 45 in the book. Let's take you down to that one. Somebody's just playing around with it. Okay, 45 says, design. The base of a railing for a set of steps leading up to the front door of a house makes an angle of x degrees. So we can see that down here where the mouse is at the bottom, x degrees. With the horizontal, let d of x be the horizontal distance between the two ends of the base of the railing. Okay. If the upper end of the railing is 5 feet higher than the lower end, find the positive number a such that d of x equals a times the cotangent of x, and use your function to find the length of the base of the railing if the angle is 35 degrees. This is number 45. So I'm just going to redraw this graph here. I said the angle's 35, and we want to know a, this d of x. And we can use the cotangent function because we have the opposite over the adjacent. So opposite over adjacent is tangent. but they said to use 5 times cotangent of 35 will give us A. Because they said the function d of x here, d of x is equal to A times the cotangent of x, and we know A. Find the positive number A such that A times cotangent of x measure. Okay. So this is A over cotangent in our case is 5 over d of x. And that's, so 5 is actually equal to A. So we are going to find the length of d of x by taking no, the cotangent is actually d of x over A. That's why A times cotangent of x equals d of x. Sorry about that. And we know A is 5. We don't know the length of d of x along the base. So we can take 5 times the cotangent of 35. So 5 times the cotangent of 35 is the same as 5 times 1 over the tangent, because we have to use the reciprocal here of 35 equals d of x. Oh, and I already put that in. So 7.14. So that distance is 7.14 feet. Now, we can use the cotangent function in Desmos. It's just my calculator. I have to use the reciprocal functions. So if we go to Desmos, we can put in 5 times the cotangent of 35. And it doesn't know degrees. You know, the only reason I can use this is because my mode is in degrees. So I guess I'd have to play around with it to be able to use degrees in Desmos, but we can do it in my calculator. So I'm going to show everybody how to do that again. So my mode is in degrees, so I can use degrees. I'm going to do 5 times, so 5 times the parentheses, 1 divided by, because I'm using the reciprocal of tangent of a 35 degree angle, and it's about 7.14 feet. Excuse me. There you go. So that's all for the graphing. Catch me back for 5.7, which is all about the inverse functions of the trig functions, and that gets fun. So